Researchers developing a survey to compare the proportions of children who come to school without eating breakfast in 2 low-income elementary schools. 80 students from school 1, 19 of them had not eaten breakfast. 26 had not eaten breakfast out of the 150 from the next school. They give you the total of students in each school, so you can do that 10% rule. Do these data give convincing evidence of a difference in the population proportions? Carry out a significance test to support your answer. So I jotted down, not the whole entire problem, I just jotted down the important stuff. So it'd be probably best if we had decimals to use those. 2.3 something, but I think I rounded up to 2.4. Does that sound okay? 1.7. Got it. Love it. Now, for a significance test, we got to do hypotheses and decide what we're measuring. And before we can even do that, we should make sure HO and HA. Yep, these are going to be still proportions, so no means for these ones. Yep. And let's go through random.
Yes.
Says it?
Yes, there is.
Good. Independent, is it the 10% rule? Sure. How about normal? This is a new problem, right? So the normal, there's going to be a different result than all the other ones. So we want to make sure that we're going through and doing all the different combinations. 24% of 80. We need the opposite, which is 76% of 80. 17% of 150, and the opposite, which is 83% of 150. Give convincing evidence of a difference. Okay, so you want it to be what? 0. The difference is 0, is what you're trying to figure out. Is the difference 0? Then there isn't a big difference between the two. If they work out to being where one's minus the other works out to being 0, then they're equal. What?
Any change.
Any change. So doesn't equal 0. Any type of difference that ends up happening for that one. The standard deviation is not the formula we used at the top. So before we even get started, we're going to use a standard deviation of what's called pooled data. So instead of, because remember for this one you're supposed to be using the HO for all of your standard deviation within there. So it's kind of hard to pick which one we're going to be doing. You're going to use pooled data. What do you think pooled data means? Bringing them all together. So how many people were surveyed all together? 230? How many people didn't eat breakfast combined? 45? And what's that? 45 out of 230 work out to being in the decimal. 0.195? I'm going to stick with 0.195. So a lot of times you'll see it's put together like PC, which means the count of successes, if you want to write down what we just did, combined over the count of individuals combined. And that's where that 45 out of 230 came from. The standard deviation formula is PC and then 1 minus PC over the count for the first one plus PC 1 minus PC over the count for the second one. So it's a little bit different than what we've been doing because you don't put each individual one within there. You use the combined, the pooled information for both of those, except for the ends. The ends you keep separate. And I don't know if I found anything on that formula sheet that says this. All right? So you'd want to put in 1.95, but then what's the opposite of 1.95? Point what? 805, sounds good. And that would be over N1. And it will get the same answer if you accidentally put N2. Let's see, there was 80 for that first one, right? Because technically, if you were to add these in a different order, it wouldn't really matter. So that's not really what the big deal is. But you just don't want to use a pooled count underneath as well. Is this 150?
Yeah.
0.05 she's got over here, 0.05. I got 0.055.
Yeah.
I just wrote the whole thing, but if you want to stick with 0.055, I would. I don't know if I'd round it up to 0.06 just because it's going to be a little bit less accurate. So I'd be careful. It's okay if you did, and especially over here, think about this, it would be 0.20 and 0.80, and so it would be a little bit different when you go to do these problems, but I think you want to try to be careful of how many decimal places, although there's nothing set in stone as to how to round. Okay, so our z-score, because a stats test is like a giant z-score. We have our hypothesis, we have our null hypothesis, our alternative hypothesis. Think back on how we do these z-score, or these significance tests. The HO goes at the end here. That's what you kind of expect to receive. So that would go at the end. This is what you're getting, and that's what you expect to get, your expected value. So we know our standard deviation's underneath. Now what should go up top there? 0.07, where'd you get that number from?
The difference.
Where did it come from?
It came from up top.
So when do we use the pool then?
The pooled is just for the standard deviation underneath.
Okay.
So this is the formula that Brandon was working with and others were working with.
Why did you put plus 0.07? There's nothing in front of it.
I was putting it negative by accident. I did another problem before that had a negative, and I was just thinking negative for it, but I just wanted to correct my mistake, so I've made it plus. And this is where your HO is going to be going. And this is your whole big old standard deviation goes with PC. So really, I think it's like 0.07 over the standard deviation is really what it ends up being. And then we got to find out what that is in the table. 1 point, yep. I used 1.264, and then that didn't help me round up, so I just used 126, but it's up to you how you do it. Because it's not really imperative that we get the exact same answer. We can be a couple hundredths off. It's not going to change too much. So you want to look in the chart to see what 1.26 is. This is going to give us this information. It actually is going to give us all this information. We're looking for here, and we're looking for here, these borderline problems. Yeah. So we're going to take it away from one and double it. Absolutely. I think I'm going to flip the page. I did Z is 1.26, and so I think I got 8962.
Yeah.
Right? Which then I had to do 1 minus 8962. And times it by 2. Because we're looking for, it doesn't matter if it's greater, it doesn't matter if it's less, we want to look for a change. So since our p-value is greater than alpha, I make it like a messed up infinity all the time. Let's see. We fail to reject. Be careful about saying the word except. I wouldn't even use the word except at all. We fail to reject or we reject. Those are the two options that we have. The null hypothesis. Now in context of the problem.